I'm Yesilin. Here I'm going to show you the solution of question 1 in homework 11. Question 1 provided as the stochastic process x of t is real WSS with autocorrelation under power spectral real density S. Ask us to show that the autocorrelation is real and even. From the condition of the question, x of t is real WSS. We can figure out that its autocorrelation is its autocorrelation function Rxx of tau will equals the expectation of x of t plus tau multiply x of t. This is also real. To prove that Rxx of tau is an even function, we need to write Rxx of tau equals Rxx of minus tau. That you can figure it out through this process. It equals Rxx of t plus tau and t, and it will equals x multiply x of t. Equals it will equals the large the expectation of large x of t multiply x of t plus tau. And this will equals Rxx t plus tau, and this will equals Rxx of minus tau. So we have proved that Rxx of tau is even. Now we come to question B. Question B asks us to prove that the spectral density Sxx of omega is even and non-negative. From its definition, we can first write the expression of the spectrum density. Multiply the E minus j omega t d tau. This can be continuously write into. We can write this part into the cosine omega tau. It will equals the same part as the before, and multiply the cosine omega tau d tau, and this will equals j Rxx of tau multiply sine omega tau d tau. And this part is an odd function, even function. We have proved it in the previous question, and the sine omega tau is an odd function, and so when this one multiply this one, it will be an odd function. Now we continue to calculate it. So the function will be twice of this part, the integral from 0 to infinity will equals Rxx of tau cosine omega minus omega tau d tau. And this is, according to the definition, this is equals to Sxx of minus omega. And so we now get proved that the Sxx of omega is even. To discuss the to prove that the Sxx of omega is non-negative, we can discuss from this system, that is x of t pass ideal bandpass system, while the h of omega equals 1 when omega 1 is less than omega 2, and elsewhere the system will equal 0. We can find out what we need from the expectation of the y of t square. The expectation of y of t's absolution square will equals 1 divided by 2 pi multiply the integral from infinity to from minus infinity to infinity of h of omega square multiply the spectral density function under d omega, and this can write into this expression. We can see that area of the spectrum density function is in anywhere is non-negative. This is possible only itself is larger than 0 everywhere, and so now we get proved.